All right. So I'm gonna start by going through together the workshop program. So there will be a first introduction by myself to give an overview of the task, but also of the technical stages that large thermal energy storage are usually going through, and as well as going just giving some economic order of magnitudes based on the IEA energy storage test 39 deliverables. Afterwards, we're gonna through 4 concrete examples of LTES technologies, ATES, PTES, TTES, and PTES. And we're gonna go through different phases of the project, so technical feasibility, design, tendering, and monitoring, as well as some economic aspects for each of those technologies. And on top of that, we'll have a presentation from Benjamin about the optimized integration of thermal aquifer storage in district heating systems. Yes. So just to give a brief introduction of an overview of the task. So the goal is to accelerate the uptake of large thermal energy storages. And the task is divided into 4 different subtasks. The first one is goal is to further improve numerical simulation, to have better tools to design the system, but also the integration, and just overall optimize the system and operation of the storage. Then the second task is to broaden up the LTES material database and test methods. The third is to set a basis for future standards and performance check for LTES system. And the last one is about disseminating information and training material, as well as the deliverable and key takeaways of this task. And basically, this webinar is part of the subtask 4. But overall, it's a 4-year project gathering 22 partners from 7 different countries, like Austria, France, US, Germany, Denmark, Sweden, and the UK. For the presentation, if you have any questions, there will either be time at the end of the presentation, and I will let you know if we have time for that. But you can feel also free to just fill up the form, and we will take those questions either usually during the planned Q&A sessions. And Geoffroy will share the link of that in the chat. If you want some more information about the task or the previous sessions that we've organized, either webinars or Q&A, please go to our website and you will see all our recordings, presentation, and answers to different questions that we've got so far and answered during the Q&A sessions. I will now give a brief introduction about the 4 main technologies that are gonna be used as examples for today and that are part of the task. So the first technology is a steel tank, either on the ground, or the most common technology is above ground, which is used to store like water, hot water, that can be charged and discharged. A similar technology is the pit thermal energy storage, which is basically the same system with diffusers, but just in a pit, basically. With the one main characteristic is that we dig soil out and we put it on the side, so that we keep a soil balance. Then there's the borehole thermal energy storage, with where we basically use the soil and the ground basically to store heat, and then the aquifer, which is based on, as it said, aquifer, so the soil underwater, underground. Usually we work with high temperature if possible, so above like 100 or 120, used for daily or weekly or even seasonal storage. And the application can be diverse, so it can either be for district heating or industry. Now I'm just gonna go through, check with you the economy of scale that LTES can benefit, which is an interesting dynamic and which kind of applies for the different LTES technologies. So we can see here on the graph, so the specific investment cost in, for example, euros per cubic meters of water equivalent. And here on this axis, the storage volume in cubic meter of water equivalent. And we can see that there's this exponential curve. So which means that basically the bigger the system, the cheaper it would be. So for example, it's very much the case for the TTES here, the blue triangles, but also, for example, for the PTES, those orange forms, and also here for the PTES and ATES. We can see that the specific cost, investment cost, depends on the technologies. For example, much higher for the TTES, although TTES can only be built for smaller volumes, so usually less than 50 or 60 thousand cubic meters, while PTES can reach usually lower specific costs, which is also thanks to the fact that they can reach very high volumes. I also would like to note that those costs are not necessarily up to date, because it's a kind of a fairly old reference, and inflation has played a role since then. But it's just to give you an overall idea about the dynamic and the economy of scale that LTES would benefit. LTES usually, the implementation usually takes place in 4 main phases: the opportunity phase, design, tender, and the 4th being the implementation and operation. So the first phase would be about, so its opportunity. So the main goal is to assess the viability of the LTES system within a specific context. So starting with gathering information about the district heating network, the geology, for example, the boundary conditions, and also some rules and regulatory constraints. It would also consist of preliminary checking for several sites, and of course, preliminary techno-economic calculations. Then the second phase is the design phase, where the idea would be to basically go deeper into the numerical like simulations, so analyzing of the district heating data, running some more or less thorough feasibility studies, and run some sensitivity analysis on the key parameters that are a bit uncertain and can have an impact on the conclusions. And obviously starting to really define the sizes and the technical specification of the storage. Once the storage is fully designed, there would be the tender phase, where basically the idea would be first to finalize the technical specifications, but also to prepare the tender documentation, and then to gather offers from different suppliers, assess them, and select the best one, and finally sign the contract. Regarding the implementation phase, so basically the first phase part would be to basically build the storage system, then to commission it, and then to take care of the operation of and maintenance of the system. So this slide basically gathers the different steps, so opportunity design, tender, and implementation and operation, and the different technical stakeholders that are being involved throughout the project. So we can see that the project owners, financing, stakeholders, and developers are basically involved from the beginning until the end. The district heating operators do play a big role. They are usually involved from the beginning, design, not really during the tendering phase, but they are obviously very much involved during the operation of the storage. The LTES experts are a bit involved in the opportunity phase, but especially during the design phase and the implementation. And finally, the general contractors are involved can be involved from the design, but especially the tender and the implementation and operation. So thanks a lot for your attention. You can feel free to just download the deliverables of task 39 that I took inspiration from to do this introduction. And if you don't have any question, we can simply move on to the first presentation from Bas on the ATES system. Yes, Patricia.
Yeah, I have one question. You mentioned that the district heating operators, they are involved in the preparation or design of the storage, but are they also involved in the operation, or is the situation that the district heating owner is the operator of the storage, or it is external company? How it looks like?
I think it very much depends on the project. They can be involved. Depends also on the integration of the storage. I think it very much depends on the project. Geoffroy, do you have a comment on that? Maybe.
I think some other experts would be even more relevant. Alex, maybe, if he's online.
Yeah, I can try to answer. If the district heating company is the owner of the storage, then they will operate the storage. But there's also it's also possible to have, you could say, a third party as owner of the storage. And if you do have that, then the operation might be the third party. But it's difficult because if you have a system with different producers, then you have to optimize the total system, and the storage is the optimization. So you have to be careful if somebody from outside shall operate.
And are there any examples of such a system when an external company is operator of the storage and delivers the heat to the network? Do you know such examples?
I don't know such examples, but I know that somebody has it as a concept. They want to implement it.
Thank you very much. Thank you.
Thanks for your question. Is there any other question? If not, I guess, Bas, I can see you already there. Yeah, feel free to share your screen and go ahead with your presentation.
Thank you very much. Second. Yeah, it should be in the presenting mode.
Yes.
Okay, thank you very much, and also for giving me the floor to tell more about the reference project which has been made in the Netherlands. It's the Middenmeer project, where we make use of aquifers to store high temperatures on a large scale. So today you also invited me to tell a little bit more about the technology itself. So I will start with a short introduction about ATES and then explain how we have developed this project from a technical design, tendering, monitoring, and also I will dive into the economic aspects. Maybe first to start to introduce myself a little bit. I'm not sure if everyone knows me, but I'm Bas Gottschalk. I have my company TTES, which stands for Dutch Thermal Energy Storage Solutions. So I'm a Dutch consultant, experienced already 17, 18 years in ATES systems, partly in the Netherlands, but I'm especially focused on the international export of the ATES technology. So therefore I work for a project in Europe, especially also in Ukraine to help with the rebuild of the country, but also in Asia, Japan, South Korea, and also in other countries. So the focus is on the ATES systems, and my role is especially to set up the project, to involve the right experts, to develop ATES in your own country or develop the business in your own country. So Romain, you already mentioned about the 4 major large-scale heat storage technologies, and today I will dive into the Aquifer thermal energy storage. Show my laser. That's this technology. We will focus on a temperature range for the mid-mere case to about nearly 90 degrees. And in the Netherlands, we define high temperature a little bit higher than the normal temperature. So we say between 40 to 90, but that's not a limitation. It can also be still larger than that temperature range. Now let's go a little bit in more detail to what is ATES, how is the basic principle. The basic principle is that you have a setup of 2 wells which hit an aquifer where a lot of water is present, so you can make use of the water as carrier for heat and cold. And in one season you abstract from the warm well and you heat up the building by the warm water, and then you return the cold of the building back into the cold well, and then you can create a big cold bubble. And in the warm season, in the summertime, you abstract from the cold well and you can cool down the building and you return the warm water in the warm well. And by doing this, you create 2 bubbles, one with warm water, one with cold water, which can be used in the next season. So the ATES is in fact a battery of heat and cold. Typical temperature ranges are for the cold well, we create bubbles of around 5 to 10 degrees, and in the warm well between 13 to 70, 25 degrees, depends a little bit on the project specifications. Typical depths for the aquifers are between 40 to 250 meter, and then of course you need to check what is the best aquifer to apply it. And typical flow rates are between 25 to 250 cubes per hour. Smaller is of course possible, but then the economics of a system will be reduced. As also Romain already mentioned, bigger systems are economically more attractive to apply. Now, when you apply the system, the interesting part is that by using the cold water, 5 to 10 degrees, you can directly cool your building. And that means that you need a very small quantity of electricity to cool the building, so that generates a very high coefficient of performance between 30 to 40, which means 1 part of electricity you can generate 30 to 40 parts of cold. But when you use it in a heating mode, you abstract warm water of about 15, 20 degrees, and that's not high enough to direct heat your building. So that's why you need a heat pump to increase the temperature level, but the heat pump reduces the coefficient because the efficiency of a heat pump is around 4 to 5. So then one of the questions we had is, so can we also increase the performance in the heating mode by skipping the heat pump in the concept? And by doing this, we created a project where we stored about 40, 50 degrees so that we can have a direct heating of the building, which already improved the economical efficiency of the system. And then we had the question, okay, but if we can store a large quantity of heat, can we also store larger amounts of heat as a buffer? So in this overview, you can see that the actual most common ATES systems are running between 5 and 25 degrees. Then we have the range where we can skip the heat pump and we run between 30 to 50 degrees. And we also define high temperature ATES, which are temperatures far above 50 degrees. And another reason why we have this definition is that for the high temperature ATES, we use other materials, water treatment, etc. So then you have also a more complex system, higher investment compared to the middle range temperature ATES systems. So as told you, we skipped first the heat pump, and then the question came, can we also store large quantities of heat? And that's expressed in its bar tube figure. So in summertime, then there's often a surplus of heat, but in wintertime we need more heat. So the concept is, can we store it in the aquifers and reuse it in the next season? Now that is expressed also in this picture. And then we find out that there are various sources which can feed the high temperature ATES system, and that you also have various type of users. So sources could be deep geothermal wells, which can produce year-round geothermal heat. It can be solar collectors, which especially produce heat in summertime, but also waste heat, industrial heat, sometimes power to heat, the conversion of electricity to heat, but also the production of electricity by CHP, combined heat and power, which also has a rest stream of heat. It can all be stored in the high temperature ATES system and then be reused by end users which are connected to district heating system or greenhouse or whatever you want. So coming back to one of the questions which was asked earlier, this system is really a business case improver between sources and users. So on itself, it's not directly a very economical attractive system, but especially in the combination with other energy users and sources, it can become very interesting. The project I want to discuss today is about the Agriport, the Middenmeer project. It's a high temperature ATES system developed for the end user greenhouse. We have made the filters at a depth of 362 to 382 meter, which is quite deep. We have one tepid well, cold well, and warm well. The maximum infiltration temperature is 87 degrees. And the maximum flow rate is maximized to 150. And with these specifications, we store about 27 gigawatt hour per year, or that was at least the capacity of the system. And then we can produce about 20 gigawatt hour per year. Now the focus for today is to look at the different stages, how to develop such a project. So we have defined a workflow, which is starting with the feasibility phase, the opportunity phase, design and permitting phase, realization, and the exploitation phase. Now, and the feasibility phase is extremely important, and it often goes through this order. First, to have a first quick scan, is it possible, yes or no? Then, of course, we will dive in much more detail to the geological situation. Check, is it also feasible from a legal point of view? what are the layers, a desktop study will be done, etc. The system concept, how will the system be used, make a kind of pre-design to define if the system is interesting to realize and construct and operate. We do a test drilling to take away some of the construction and also exploitation risk to get better design parameters for the next phase. Then, of course, we will update our first initial study, and then we move on to the design phase. Now, that will be continued in the next phase, and then we also have the permitting phase. We detail the design, and then we go to the construction phase, and finally, of course, the exploitation of the whole system. Now, we'll go in some more detail to the project itself. Here we have the Netherlands, Amsterdam, and then Middenmeer is more to the northern part of the Netherlands, but on the west side. There is a kind of area which is owned by a company who provides all the electricity, gas, water, everything which is needed for especially farmers, greenhouse farmers, and also a lot of data centers are present in this plot. They have developed a number of geothermal wells, and they are still going on with that to provide enough heat to the greenhouses. And then here in this corner, they have constructed the high temperature LTES system. And here you see the greenhouse itself, the hot well, the test drilling, a monitoring screen, and the cold well. Now, when we have a look at the cross section, you will see we make use of deep geothermal heat from the Slochteren formation. It's a sandstone from about 2.45 kilometer. And then we store it temporarily in the high temperature LTES system at nearly 400 meters. Now, how did we start? Of course, with a lot of discussion with the client, the end user, but then first, of course, with the desktop study to analyze how does the subsurface look like, where are the layers, sand layers, clay layers, because they are very critical, because we need the clay layers as a kind of insulator above and below the target aquifer, because then the heat will be insulated and on its place and don't move too quickly to the subsurface. So that's why we said, okay, the fourth aquifer, the yellow one and the green one are the most promising one. Then we started with the test drilling itself. This is the middle one. We drilled to nearly 500 meters, installed a number of meters and screens to do testing and to analyze the properties of the aquifers. And from that, we concluded that the fourth aquifer, the yellow one, is the best one to apply. And in these considerations, we know that the well capacity itself has a big impact on the investment cost of the system, because if you have a small capacity, you need more wells, more investment, and the storage efficiency has a big impact on the operational cost. Now, both are influenced by the thickness of the aquifer and also the permeability, and the clay layers is an indication how good they will act as an insulator, so the thermal efficiency will be determined by the clay layers itself. Next important step is to check how the storage will be used, how do it be connected with the district heating system. Will it be a solar system or will it be interacting with the deep geothermal? It is, of course, it's not that the deep geothermal water is injected in the high temperature, so we only inject the higher temperatures, but not the water itself. Another very important part is what are the temperature levels you are working with. So what will be the injection temperature of the high temperature ATES system. And if you start to abstract, till which temperature do you go? Because if you can still use 70 degrees or 60 degrees or 50 degrees, then you can see that the longer you can use your ATES system, the more energy you can harvest from your storage system. But at a certain moment, you come at a point that you cannot deliver enough heat to the end user, or the end user should maybe use an additional heat pump to increase the temperatures again. But that will cost more electricity, so also yeah, has an impact on the business case itself. Now, this kind of parameters are very important in the modeling we do for a project, and has also a very big impact on the economical benefits of a system. And therefore, it's recommended to start with this process in the early stage of a project to have a feeling, okay, how can you use the ATES system within a source and an end user of heat. Now, of course, you also have to take care for the legal aspect. You need a permit in the Netherlands for applying that. So when we had more information, we have done thermal and hydraulic modeling of the impact of the ATES system for a 20 years or 30 years operation of the system. And then you have to prove that there will be no negative impact on the environment, on the water quality, on microbes, etc. And that's something you need to discuss with the authorities. And if it's fine, then you can get your permit. So there are some standards or a template of conditions how to do that, and that's a very practical guideline to get a permit. Now, I want to highlight some of the important design aspects. The first one is that when you increase the temperature, then you have a bigger risk that calcite will precipitate in your wells. And that's something you want to prevent, because you want to prevent that the wells will clog. So one of the solutions is to add acids, and we are choosing for the CO2 dosing, because that's not so complex as other acids, and that works pretty well to prevent that the calcite start to precipitate. The second important aspect for the Middenmeer project was the risk for clogging by sand production, because we had a very small layer, so we exceeded the norms a little bit, and we abstract with a higher flow rate than we normally do for ATES projects, because we needed more capacity. And therefore, we had a continuous sand filtering system. Here you see some of the examples. That was in the early beginnings, so that's not normal, for preventing clogging by sand. We have also seen, here you can see in the middle picture, the heat losses by the casings, because when you start to abstract at nearly 400 meters, you will see that all the heat which will be abstracted will be also partly go to the other formations. And we saw that the impact was small, but finally we come to the conclusion that it can be around 10%, and that's quite significant because we have high amounts of energy which we abstract and inject. The fourth point is that we had to select other materials than we are used for ATES systems. So for ATES, we often use PVC, but that starts to become weak and melt at temperatures above 50 degrees. So that's why we chose for piping, which was the glass reinforced epoxy wells, and also stainless steel filter screens at the bottom. You also have to consider which type of pumps do you need, because you have high temperatures, nearly 90 degrees. So in this project, we selected electrical submersible pumps, because the client was also familiar with deep geothermal wells. So then it's common that they use ESPs, and that's why they also said, okay, please choose that for this project, because then we have the same type of pump which we know. Now here you see some examples of the drilling itself. Here you see the drilling in progress. This picture we installed the pump, and here you see just below the wellhead you see the injection pipes, and here in the middle you see the abstraction pipe for the water. Here's the final wellhead with all the equipment, with injection units and pressure regulators and some other measures. Here you see the CO2 dosing unit. Here you see the filter screens where we continuously filter the sand or take out the sand. And in the last picture, you see the heat exchangers for this project. Monitoring is, of course, an important point. So the test drilling has been completed and finished as monitoring screen. So that was nice because then you can make use of all the screens. We installed fiber optic cables for temperature measurement. Here you see a screenshot of the results. We analyzed for macronutrient elements of the chemical composition. We also measured ATP to see how the microbiology is developing in the wells. And that first has sometimes an obligation from the permit point of view, and we also want to learn more of this project, and that's also why we have an extended monitoring. Now the last slide is more about economical aspects. Two pictures I want to show you. The first picture, you see the blue line, which represents the first cycle, orange second, and the other one is the third cycle. So first, second, third. And what you see is here the abstraction temperatures from the hot well. So after the first load, we started to abstract with temperatures around 65 degrees, and then you see that the temperature will decrease quite rapidly. And that's logic because we have a relative small hot bubble, so it will empty quite quickly. But in the third cycle, you see that our bubble has become much more bigger, better loaded. So then we can start to abstract with temperatures nearly 75 degrees. And you see that you can extract much more cubic meters before the temperature goes to drop. So here you see that the heat losses are smaller due to the bigger bubble we have. Now, in the right picture, you see the calculated efficiency numbers. So the gray ones are the predicted ones. The red ones are the actual ones, and they're slightly smaller in the first years. Why? Because we just stored smaller quantities of water, which resulted in more losses and a smaller efficiency. And there was one in the last year, there were also some heat losses extra. So and there was some issue with the delta T. So that's why we had a little bit smaller ones. But if you recalculate it to our original starting points, then we see that we are quite fitting the efficiency curve as we has predicted before. Now, the conclusions is that this system has been designed and constructed in a nice, proper way. So it's running already for more than 4 years without any serious problem. So we are very happy with that because it was also for us a quite, learning project because nothing was done before. So we have to figure out nearly everything. Also, we are no clocking and by scaling or sand particles. So that's very good because then the measures has been effective. The CO2 dosing helps and also the sand filtering works well. And we could, of course, retrieve the heat. Lessons for other projects is, we highly recommend to do a test drilling. It's upfront cost, but very helpful because it gives you a lot of insights and also gives you design parameters, reduce the risk for the construction and also for the exploitation. System integration is very important. Bigger is better. You have to have a proper look at the materials and equipment. Thermal insulation of the extraction pipe will be very helpful to reduce energy losses. And also be aware that there are more high temperature ETS developed at the moment. So this within the use for heat program, we developed the Andal, which is around 50 degrees, but also TU Delft is developing a high temperature ETS at higher temperature levels. So be aware of that. So thank you very much. I hope I'm still within the time frame.
Yes, 1 more minute. Perfect. Thank you so much. We have a tiny bit of time for questions. I saw that there is already one in the chat by Patricia. Maybe you want to ask your question yourself.
Yeah, it was, you mentioned that there are around 10% of heat losses in the transportation, water transportation. The question was whether it is procedure to use pre-insulated pipelines to avoid these losses, those losses. Thank you.
Yeah, it was considered in the design phase, but finally it was complex, cost increasing, and we calculated it in the design phase at 2-3%. So that's why we said finally, okay, we will skip that part. But we are now in another project where we highly recommend to the client to insulate this, to insulate the pipes to prevent the thermal losses. So that's also why it is a recommendation for us to other projects.
And how do you do it? Do you use like the pre-insulated pipelines, or you use kind of a special insulation for this kind of
That's also a good question. We are doing some research to that because insulation is often quite light, lighter as a lower density than groundwater. So if you want to install a pipe, then you get a lot of upwards forces, and that's something where we are checking, can we have more heavier insulation or heavier pipes, thicker pipes, iron pipes, to compensate for the lighter insulation material. So it's still a part of where we are working on today.
Thank you. Thank you very much.
All right. Thank you very much for your question, and Bas for your answers and presentation, obviously. I guess it's time to move on to the next presentation by Benjamin.
Yes. Thank you very much for having the chance to talk here about our project Aquifer, which stands for Optimized Integration of Thermal Aquifer Storage in District Heating Systems. In our project, we focused on the German case, and today I will only present part of our results, focusing on the ATES potentials in Germany. Short overview, what will I talk about? First of all, I will give you a short overview of the overall project, the different topics we addressed, and then present the methodology for the assessment of the ATES potentials, present the key results, and give you some key findings from the research we've done in the last about 3 years. In our project, we focused on the 3 geothermal regions in Germany, so the northern German basin, the South German Molasse basin, and the Upper Rhine Valley in the southwest of Germany. And the project was organized and led by the Hamburg Institute. They also focused on the design and development of storage systems. Our project partners were furthermore the Friedrich-Alexander University of Erlangen-Nuremberg, focusing on the geology and supported by GTN, a drilling company from northern Germany. And we at ERCO Institute, we focused on the storages in the district heating systems, and thereby focusing on dispatch modeling and assessing the behavior of all the different components in a district heating system when ATES is integrated. In each geothermal region, we also had practical partners. We integrated district heating companies in our research project, one from Hamburg for the northern German basin, one from Augsburg for the South German Molasse basin, and from Freiburg for the Upper Rhine Valley. The main questions we wanted to address is is seasonal heat storage in an aquifer feasible from a geological and technical perspective? Of course, one essential question is, are there any storage formations available? And are they suitable for storage? And the second main question was which concepts are economically feasible? We focused in our projects on high temperature applications above 70 degrees C. In 2 of our cases, even up to 90 degrees C. Are other components needed for the integration in large district heating systems? Do we need other storages, like tank storages for higher temperatures, or even heat pumps for the integration of the ATES? And we focused on the design of reheating and boosters for a very high availability. So to make sure that the ATES system is able to provide high supply temperatures, especially in winter times. So in the project, of course, we had several iterations to design solutions for our practical partners. We did a detailed assessment of the geology in the 3 cities, doing fee flow simulations in the underground. Made a first storage demand assessment, assessing which heat generators are available today in the district heating systems, which heat generation units are planned in the future, what are the expected heat demands in the district heating systems, and trying to find out like which volumes do we need in the systems. Based on that, we did a pre-design for the storage system and then started the first iterative simulation studies to find a base variant which is most likely suitable for the assessed district heating systems. After that, we made a detailed design of different components and finalized the design phase with a large simulation studies addressing or assessing different variants and sensitivities. And based on the findings from the underground, from the design of the ATES system, including heat pumps and probably also tank storages, we tried to derive general findings and wanted to answer what are the possibilities, but also limits of high temperature ATES in district heating systems. The last part is the part I will focus on today. In this context, the key questions to be answered to assess the potentials of ATES systems for district heating is like what is the technical potential for seasonal energy storage in different district heating types? What is the spatial distribution of high temperature ATES potentials in the North German basin, the Upper Rhine Graben or Upper Rhine Valley in southwest Germany, and the Molasse basin more in the southeastern part of Germany? And what is the potential heat demand in each district heating type and available heat supply to be stored in the ATES system? The main steps and sources we did for the assessment is, of course, data collection. We tried to find out which are the current and also potential district heating areas in Germany, what are the geothermal conditions in the underground, and what are the renewable and waste heat potentials all over Germany. In the second step, we processed the data. We compared different sources for each of the mentioned potentials we assessed, and also for the geothermal conditions. We made a categorization of district heating areas, mainly based on the heat demand in the different district heating areas, and then matched and clipped and intersected all the information using QGIS. And in the last step, when we had the first, after the matching, clipping, intersecting, we generated and interpreted the results, but also defined some further research questions which need to be answered in the future. For the potential and current district heating areas and the renewable and waste heat potential, the main sources were papers from Fraunhofer ISI in Karlsruhe, in which they did a spatial analysis of renewable and excess heat potentials for climate neutral district heating in Europe, and they have or made available all the data for us with a high spatial resolution. And for the geothermal conditions, there are a lot more sources we used, also different sources for the different geothermal areas. Some of the sources already did heat storage potential assessment in different depths, but that was not available for all geothermal areas. So we also assessed the underground conditions and made own calculations and assessments of the heat storage potentials. Summarizing the results for the ATES potentials. First of all, as I said, we looked at the district heating areas in the different geothermal areas of Germany. So all the white, which you can see on the map on the right side, we did ignore and did not assess in detail. The different district heating types we defined, you can see in the table on the left side. So from very small systems with a annual heat demand of below 100 gigawatt hours to very large systems with more than 3,000 gigawatt hours per year heat demand. These are the very large ones, for example, in Hamburg or Berlin, but also in the rural area. Large systems in the geothermal areas, there are only 4, which is, of course, Hamburg, Berlin, but also Munich and the Frankfurt area in the southwestern part of Germany. And what you can also see, most of the identified potential district heating areas are very small ones, around 500 systems with less than 100 gigawatt hours per year heat demand. The renewable and waste heat potentials we assessed, you can see in the maps on the right-hand side. So we assessed the potential of large solar, thermal, but also rivers and lakes. It is gray in the table because we did not consider this for the heat storage in the ATES system. Then we assessed the hydrothermal energy, so deep geothermal potentials, waste to energy plants, wastewater treatment plants, and industrial waste heat. For each of the sources, we defined a maximum distance of the potentials to the district heating systems, which is the smallest for solar thermal with only about 200 meters distance from the system. And for high temperature, high potential heat sources like waste to energy plants or industrial waste heat, especially when they are rather big plants, the distance can be up to 20 kilometers. The maximum distance is also based on the assessment done by Fraunhofer ISI, but also expert interviews in this case. The overall technical potential is rather high, especially for hydrothermal energy. But yeah, there are several uncertainties, especially for the deep geothermal potentials, so to speak. And one thing which has to be mentioned is as I said, we defined maximum distances to the district heating systems. Some of the potentials can be allocated to different district heating systems, like if there are or when there are several district heating systems within the range of up to 20 kilometers, it's accounted for both systems because both district heating systems could potentially use that. For the underground, you can see here on the right-hand side the covered areas where we found enough data to do a first assessment of the ATES potentials in the underground. I have to say that we focused on higher depths than it was done in the Netherlands in the project Bas just described. We focused on depths between 500 and 1,500 meters for several reasons. The main parameters we assessed in the underground are, of course, the temperatures, the depth, the water density, rock densities, and porosity. The reservoir thicknesses, which is a major factor to see whether we could potentially find high enough volumes for the ATES. The effective, so usable reservoir volumes, the heat capacities, packing correction factors, and recovery factors. The main sources are listed below the figure on the right-hand side. Looking at the time, I think I will skip that. You can check the description of the different parameters we assessed when you download the slides after the presentation. What we found in the end is that there are about 570 potential district heating areas in the geothermal regions of Germany, most of them in the North German Basin, which is also the largest geothermal area in Germany. And for around 420, we found sufficient data to assess also the underground conditions. And from these 420 district heating systems, in 167 district heating systems, we found ATES potentials in the underground. With like the overall storage potential in Germany is above 700 terawatt hours. Most of this potentially is also due to the large area in the North German Basin, but also the underground conditions are there much better for ATES than in the other geothermal regions. The potentials or possible application in small district heating systems, at least from our point of view, is at least questionable due to the low amount of heat supplied to the final customers. We just saw that it is possible to also develop projects with only 20 gigawatt hours recovered from the ATES systems. But there are some challenges, I would say, when you look really at large district heating systems in cities. The numbers or the detailed assessments are presented in the next slides. Starting with the Molasse Basin, we identified 19 district heating systems, which are close enough to potential ATES areas in the underground. Most of those systems are small ones. There are only 2 larger systems which have potential in the underground and also a potential above ground, so a high enough heat demand and also renewable and waste heat potentials to be stored in the ATES. Here marked are the limiting factors. So the available heat for the storage and the heat supply to the district heating systems are higher in this case than the heat storage potential. So a maximum heat storage potential in the Molasse Basin is around 1.2 terawatt hours, which is really just a theoretical potential and in reality might be much lower. In the Upper Rhine Valley, there are around 34 district heating areas which have potentials above ground and underground, and 3 district heating systems have a potential or have a higher potential concerning the heat demand. Also here, in most cases, the limiting factor or defining the maximum potential are the heat storage potentials in the underground. Just for one case, it's the heat supply to the district heating system, which is lower than the heat storage potential in the underground. In the North German Basin, we identified more than 100 systems with suitable conditions above and underground. In these cases, the storage potential is much higher than the heat supply to the district heating systems and the available heat for storage. On the right-hand side, you see the, as far as I know, the first high temperature ATES potential map for all over Germany. Our key findings is that ATES is mainly a technology for larger systems. So we said especially for types 4 and 5, probably also for type 3, but most likely not for the smaller district heating systems. The match of all relevant requirements for ATES deployment is only we only observed in a few district heating systems with a sufficient size. So there are only we only identified 18 all over Germany. And the highest potential is expected in the North German basin. In the other geothermal regions, in only a few district heating systems, we found a high heat storage potential in the underground, plus high renewable and waste heat potential, plus high enough heat demand from the district heating systems. However, the results still need to be handled with care. So the data available for the German underground is still very limited, and therefore the uncertainties are high. I don't know if you can directly translate that from German to English, but our German geologists always said, "Vor der Hacke ist es dunkel," so it's dark in front of the hoe. So you need to drill to know if the expected potential is real. So it's comparable to what Bas Gottschalk just said. And finally, some key or general takeaways also from the other assessments we did in the project. We think that NATES as a standalone solution cannot meet the urban network requirements, or we saw, because the supply temperatures in wintertime are way above 100 degrees C, and we have a maximum temperature of about 90 to 95 degrees C in the underground. So the district heating systems, they have high power, high temperature requirements and need high capacities in the storage. But with the right design, reheating via one or more heat pumps, an ATES can offer multiple advantages to the district heating systems. ATES can be a fully fledged generator or heat generator. And also we can increase the storage efficiency when integrating heat pumps because we can cool down the ATES much more than without heat pumps. And finally, customized technology combinations are required for district heating to optimize the system benefits. So it's the combination of capacity and power of the ATES in combination with other technologies. And the question is, can we provide also peak load, so heat when it's most expensive in district heating systems? Short note, a handbook for the development of large thermal energy storages in Germany, Hamburg Institute and several other partners are just developing. It will be available late January, early February, most likely, describing different aspects also for the commissioning and regulatory framework for large thermal energy storages in Germany. Thank you for your attention.
All right, thank you very much, Benjamin. So we're supposed to have a break between 10:35 and 10:45. So the people that would like to go on a break can just reconnect at 10:45. In the meantime, I suggest that we can take questions, if that's fine for you, Benjamin.
Yes.
I saw that there are a couple of them in the chat. So yes, for example, Damien, I don't know if you're here and you would like to ask your question directly.
Hi. So
Hi.
you were saying you were thinking about at least in having tanks in the system as well and heat pumps and so on. But did you really simulate them in your variation studies or
Yes.
not? And if so, what software did you use for those components?
For the design of the storage system itself, so the ATES plus the connection to the district heating system, the colleagues at Hamburg Institute mainly did the simulation, I think, in Transys. And so they simulated different sizes for the tank storages and different combination, different hydraulic integrations of the heat pump, plus sometimes several heat pumps, either in row or in parallel. Yes.
And okay, thank you. And would it be possible to have a look at those projects? Are they open?
As far as I know, the types are not published yet, but you can definitely reach out to the colleagues at Hamburg Institute.
Okay, good. Thank you.
All right. Anyone else? Alexander, Niels, or Jörg?
If they're already in the break, I will just answer the questions shortly in the chat.
I'm here. So
Okay.
what I see in Switzerland now is we are to have more capability to use environmental heat sources like the lakes. We see a change in the district heating networks. We have like high temperature, 170 degrees networks at the moment in some of the larger cities, but they are slowly coming down. They're changing to 120 and even lower if possible. Did you notice a similar effort at the district heatings you observed?
Somehow yes, somehow no.
Okay.
So in the inner city areas, I would say that they do nothing about reducing the temperatures yet, because they need the high temperature to provide the amount of heat. And also the power needed in the district heating areas. But when they develop new areas or like connect new areas of the city, the temperatures are usually lower. Especially in Augsburg, they said like new district heating areas are usually developed with lower temperatures. And at least in one case, they are also thinking about reducing the overall supply temperature in the whole city. So there are some developments, but not really in the very big cities, in the inner city areas.
Okay.
But they are not at 170. They are usually maximum 130.
Yeah. Okay. Thanks a lot.
Cases. You're welcome.
Yeah.
All right. Niels was asking how deep drilling did you consider?
We assessed potential ATES layers between 500 and 1,500 meters. For the overall potential assessment and in the for the district heating systems or district heating operators who were part of our project, we focused on the site conditions in the respective cities. So there, the depths differed a bit.
All right, thanks. And the last question from Alexander, if he's not there, but did you include the geological option to use caverns in solid rocks for ATES in Germany?
We only focused on natural aquifers in the underground and not on the development of caverns in this case.
May I add something?
Yeah, yes, of course.
Do you think there is a potential for ATS in solid rock in Germany?
As I'm not a geologist, honestly, I cannot really answer this question. I think there it's better to reach out to our project partners, GTN or the University Erlangen-Nürnberg.
Okay, thank you.
Okay.
All right. Thank you very much.
Thank you.
Just if anyone has a question, we still have 2 minutes for that, or otherwise we can just wait for the break to end.
I had a question about the distance for a solar thermal. I was wondering a bit, it was 200 meters.
Qua sotto. Ma quelli non sono il massimo, devo dire.
one microphone is not muted in the moment. We just took the 200 meters from a source we found. Also due to the fact that temperatures are comparably low, and yeah. But would you say that also higher distances would still be feasible? Yeah.
I think so, yes. But then you have to calculate.
Okay, thank you.
All right. Hi, back everyone. It's 10:45, so Olaf, if you're ready to start, you can just go ahead.
Yep, thank you. Well, I'm Olaf Andersson. I'm glad to be here and present the Xylem high temperature BTES in Emmaboda. It was actually constructed some 15 years ago, so this presentation will also cover the results during these 15 years, but I will also concentrate on the methodology as requested. It doesn't work here.
The screen or anything? Maybe press
I can't
escape.
change picture. Now it comes. Yeah, okay.
There we are.
Yeah. Well, Xylem Emmaboda is a manufacturer of pumps. It used to be Flygt pumps. They are more famous for that, maybe, that trademark. It's quite a big industry with 1,100 employed, and the indoor area is 110 square meters. It contains a foundry and several workshops, and especially for the foundry, they use a lot of electricity. Hence, they are also producing a lot of waste heat. I'm sorry, I'm a little bit catched a cold, so my voice is not that brilliant today. So why a BTES system? Well, a BTES system is a storage system in the rock using a duct system with plastic pipes in boreholes and densely spaced. And they were thinking, if we can use such a seasonal storage to take care of the waste heat from the summer and use that to enforce or improve the waste heat usage and cut the district heating, that would be nice. It would also mean that it should minimize the usage of cooling towers, where you just let out the heat for the birds. And we believed at that time that we could do this by BTES seasonal storage. So this is a principal flowchart of the thermal energy flow in the industrial area. It does has an internal grid, let's say a district heating grid. The cooling needs, and that is supposed to be around 8 gigawatt hours per year, is coming from the melting hours in the foundry and several processes in the workshops, and of course ventilation. This is captured and has been captured over the years in different ways. In the center, you may see here, that's a water basin, a cold water basin, and that is connected to cooling towers. But instead of using cooling towers, there's a heat pump here that take care of that heat and increase the temperature to around 50-55 degrees and place it on the internal system for heating. The same goes for the ventilation, especially from the foundry. And in return, they also have air conditioning there, and that's also worth something. The melting hours by themselves, they are chilled, and it is directly used through a heat exchanger and placed in the internal grid net. Now, the idea here is to increase the waste heat usage by using the BTES system. So you store heat, excess heat in the summer, and you recover it again in the winter. And we thought at that time that we had some 8 gigawatt hours of waste heat, but it showed not to be. I'm coming back to that later. Even if this is 15 years ago, we kept following different stages, like feasibility studies, and then design, and then construction. However, the tendering was quite simple at that time. It was just using the result of a design and asking for bids. There were several contracts, one for site preparation, one for borehole drilling, and one for borehole heat exchange installation and connection, and HVAC and control, and construction control. And that was the position I had during construction. The feasibility, if we go back to that was executed in 2008. And we made this energy flow survey, geological survey, test drillings, 4 of them, TRT thermal response test analysis, test pumping. Even if it's a BTES project, we still need to know how much groundwater that was flowing through the site. We took deal of some permit issues, And of course, we made the first economic calculations, and we looked for financing also. In the design phase, we used modeling. It's a duct storage model, it's called DST. It's made in transit. So we found out the size of BTES, the location. We looked at several such, and when we had the science, we decided on the location. And then we made the outline for the whole system, which shows a special borehole heat exchanger, coaxial, you will see later. We chose a material for insulation and made a system for HVAC and control and instrumentation also. And we have an environmental assessment report for permit. And after construction, it was just put into operation. Now, as it turned out, we had two phases, one with heat exchanging only towards the BTES, and phase two, when we also installed extraction heat pumps. You will see that later on as well. And this happened in 2018. So the basis for design looked like this, and this was taken 2007 and 2008. So these are quite old data and not represented anymore, not actual anymore. But still we used that for designing the size of a BTES when it comes to energy turnover into it. So it's around 1 megawatt capacity. And the idea was to store in this area when you don't have any need for heat and use it later on when you have the need, just as any UTES should work. The model simulation, it looked like this. We assumed we had 6 gigawatt hours the first year to put in, but that never happened. We only had 2. But anyway, we expected to store 3,200 megawatt hour annually, have 30% in heat losses. We used water as a fluid, and we designed a flow rate of 25 liters per second, and a working temperature of the storage with 60 to 40. The borehole heat exchanger is a new design. It was manufactured by a plastic industry up in Borehole in middle Sweden. It is a construction with double pipes, one inner pipe and one outer. This is the inner pipe. It's a DN40, and this is DN90 millimeter. It's threaded, as you can see here, with 10-meter lengths. And we have a special construction outside here to make the water more turbulent on its way up or down. It allows reversed circulation. So this means that when we store energy, it comes this way through the inner pipe, and you start storing in the bottom of the boreholes. And then the fluid outside that has a direct contact to the rock will lose its energy gradually till it comes up here. When we reverse and take out the energy again, we just do it reversed. So we have a flow going into the borehole on the outside and the highest temperature coming up from the bottom through the inner pipe. That's how it worked. We also tested this the borehole resistance, and it turned out to be a little bit less than 0.02 meter times K W, as you see here. So that's an effective heat exchanger. The boreholes were drilled with compressed air, hammer drilling. See if we can see the number here. It's 140 boreholes with a spacing of 4.5 meter only. The depth is 150 meter. The diameter 115 millimeter. And we cover a surface of 2,400 square meter with a square shape also. And the volume is a little bit more than 300 cubic meters of active rock volume. And the thermal conductivity in the rock is 2.9 watt per meter Kelvin. The horizontal pipe system, it's plastic pipes, 40 millimeter, but we have field manifolds. That's these blue ones here. And in the overview picture, you can also see that we have separated the storage into 7 different sections, each one containing 20 boreholes, and they are parallel coupled, and 2 by 2 boreholes, and all sections are in parallel, so to speak. There are at this end here the main manifolds that takes all the pipes, collecting pipes here, 90 millimeters into 150, I remember it was. You also see here some red dots. These are boreholes that are used for monitoring. The insulation is by foam glass. We chose from many different options, but we stayed with foam glass that has a thermal conductivity of 0.4 watt per meter Kelvin. It's light, it's not very heavy. Sorry. And it's recycled glass. It's made of, it's expanded glass. And it's in a gravel fraction, as you can see here. When we come to the monitoring, so we had a first phase, scientific monitoring and evaluation. I'm sorry about the coughing. I take a sip. During this period, we stored 12 gigawatt hours of heat, but we recovered only 8% of that. And the working temperature that we thought we should use was not in sight. The maximum temperature in the rock that we achieved at that time was a little bit above 40 degrees C. And the years after, it was a little bit more up, but not more than up to 45. But the system works beautifully in dumping heat. But it was when it comes to the recovery that it didn't work. So extraction heat pump was decided.
Olaf,
And this
just for you
was
to know,
installed in
you have 5 minutes
2008.
left.
Sorry?
Just for you to know, you have 5 minutes left for your
Yes.
presentation.
Yes.
Thank you.
I do it quickly. It was 8 units of NIBE 60 kilowatt, 480 kilowatt together. But it has an actual capacity of 800 kilowatt due to the fact that we have a nice heat source. The second performance was taking place 218 to 2021. It was a part of it. Annex 52, as you can see here. It's instrumented with electricity, pressure, and temperatures everywhere. The COP was, when it just comes to circulating the fluid, turns out to be a little bit more than 150, so that's very good, and it's due to that it works with a high delta T. The COP of a heat pump system, around 5. And what happens was when we extracted so much heat again, the working temperature was down to 2040. So before and after heat pump installation, we extracted a lot of energy from the store. So this is pretty good in balance. This was prior to the 2 years prior before the heat pump. Economics, well, we invested 13.5 million SEK. We expected 2.2 megawatt hours per year with a saving of 1.3, so that makes 10 years in payback. The additional investment was paid off quickly, less than 2 years. If constructed today, it would take 22 million. And it would end up with a little bit less than 10 years payback. The conclusion is that this heat pump rescued the storage facility that still works beautifully. Thanks for your attention.
All right. Thank you so much, Olaf.
Thank
and also
you.
for respecting the time. So we have actually 2 minutes left. So if anyone would like to ask something, we can take it now and then the rest during the break.
Il y a des questions. There are questions in the chat. I think we'll start with this. Robert is asking, is the BTES still in operating? I think the answer is yes.
I'm
Olaf?
sorry. I really didn't hear that.
The first question was if the BTES in Emmaboda is still operating.
Yes,
And I'm
it
guessing
is.
that the answer is yes. Yeah.
Yes.
And then there was a second question on where was the foam glass insulation applied?
It was applied on top of the cover. It's a 1 meter cover of which 20 centimeters is sand, and there's a plastic geotextile on top of that. And then comes the insulation that's 40 centimeters thick. And it goes out not more than 5 meters along the on the sides, so to speak. It should have been broader.
Okay, thank you. Maybe I have a question. So after this, you started using the heat pump. Did that change the operational temperature for the boreholes?
Yes.
And what was the temperature level then?
40-20, it works now.
Okay. Whereas
So
before you were
when
able
it's-
to go to 45.
No, not really. It's no use when you have heat pumps for extraction. The heat pumps works with 20 or 25 on the evaporator side. It can't go further up with these heat pumps that we have. So
Okay,
it's
thank you.
a little bit recirculated, so to speak.
Thank you, Olaf. There is a couple of more questions in the chat, but we will maybe ask you to stay during the break if you can, Olaf, to answer them.
Yes.
And
Are
we'll
they on the
switch to
chat, so I can.
yeah, they're in the
also-
chat. Maybe you can answer them in the chat if you want. Yeah,
Yeah.
that could also be an option.
Yeah.
And Julian, the floor is yours in the meantime.
Okay, thank you very much, and hello from my side as well. Let me quickly share my screen. That will probably help. Yes, so I'm here today to tell you a little bit about our heat storage project in Berlin. I'm from the Berliner Energie und Wärme, so the municipal district heating company in Berlin, which we heard before is one of the larger district heating systems in Germany, or the largest. Here you can see right now in the background already the large tank storage I'm talking about today at our power plant site Reuter West in Berlin. But a quick introduction on our company. So the BEW operates the largest district heating system in Western Europe. We have roughly 2,000 kilometers of district heating network, about 8 terawatt hours of heat sales, which supplies around 1/3 of the Berlin inhabitants with heat. We have 9 large generation sites with combined heat and power, but many more smaller ones, and installed capacity of about 5.5 gigawatt plus 2 gigawatt electrical capacity. So this is the background of the system I'm talking today, and here you see this double plant site of Reuter West and Reuter, which I'm talking about today in the western part of Berlin. The overall context of our system transformation, I think every European district heating company is working on right now, is our final goal of 100% renewables here in 2045 by regulation, and we already made a first step in 2020 by phasing out all lignite generation and increasing renewable share to 7%. And now currently we're on the next milestone to 2030, where we will reach 40% renewable energies and waste heat share, and have the large task of hard coal phase out, which is especially important for the power plant side I'm talking about today at Reuter, because there we have about 700 megawatts of hard coal CHP still in operation, which needs to be replaced by other generation capacities. So this is the Reuter or Reuter West. Actually, what's here in green is only Reuter West. And here on the right side would be the second power plant site, Reuter. But here this is one of our major transformation sites for this step until 2030. As I said, we have 700 megawatts of coal capacities which need to be replaced. And that's a lot which cannot be done by a single technology today. So we have a large mix of different technologies, which is a very nice use case for heat storage, obviously. You see we have a biomass CHP, which is under construction. We have the heat storage, which is already constructed and in operation, but a waste to energy steam turbine, which is upgraded to have a higher capacity using the heat of the waste incineration plant on the other riverside, and a large wastewater heat pump, which uses heat from the wastewater of the plant on the other Spree side as well. In addition to that, we have here a power to heat boiler, which is already in operation as well, which together with our heat storage can make a quite nice use case for storage. But overall, the storage is not just meant for this power to heat, but for the whole plant side for the optimization. And in addition to that, which is quite important and a lot of effort as well, if you have a lot of different new generation plants, then you already need additional projects for the adaptation of the hydraulic infrastructure, the electric infrastructure, and the building place as well, and decommissioning and deconstruction of the old sites. So now let me get into this heat storage project, which you can see the final storage here on the left side. It's about, in total, it's about 54,000 cubic meters, but only 52,000 cubic meters is actually filled with water constantly. And so that's the net storage capacity, which made it the largest tank storage in district heating when it was in construction. I don't know if that's still valid. So let's say it's one of the largest storages in district heating. It's about 38 meters high, which is important design aspect, which I'm gonna come back to a little bit later. We can store about 2.7 gigawatt hours with a loading and unloading capacity of about 200 megawatts. That's always a little bit changing depending on the actual operating temperatures, but that's about the design capacity, which leads to a full unloading and loading time of about 13 hours, so roughly half a day from full to empty or otherwise around. The storage is atmospheric, so it's not under active pressure, which resides in a maximum temperature of about 98 degrees. And since we have here this quite nice height of 38 meters high, we can use it for static pressure holding function for our district heating system as well. So this means we can replace another pressure holding system by this passive function of the storage, which is an additional value to our project. The total cost, including all design, connecting pipes, equipment, and the storage, amounted to 50 million euro, which is higher than what you would expect when you only look at the specific numbers that we saw earlier in the introduction presentation with this regression curve where you have the specific storage costs, but this is the total project costs, which is always quite a bit higher than the specific costs of the tank only, because more than, in this case, more than half of the cost was for the pumping plant, the connection, and the overall surrounding system. For the construction, the project, we divided this work into 3 lots. The first was the civil work, so we had the heat storage plant, which is about 400 meters away from this heat storage, the connecting pipes, and the pump station. Then the second one, obviously, the tank, which you can see here, including this design, construction, and erection of the heat storage, which I said was less than half of the total costs. And then the process part, where we have a general contractor for the engineering of the pumping station, for example, and the auxiliary system, and the commissioning of the system. So here is a very, very idealized schedule of our project because it has quite a bit of history, and I wanted not to go into too much of detail. First of all, as you see here in the planning phase, there's an arrow pointing to the years before this project, which is because the idea of the storage dated back to around 2011, so quite old, and was started but then put on hold and restarted a couple of years later. So part of these works, which are summed up here in the planning stage, already date quite back a little bit. The start, obviously, is the concept development and the analysis, which is what my department does. So we look at our power plant sites and see how to develop it further, how to replace old plants that go out of work. Usually you have the site selection as well. In this case, it was quite obvious because we had to build something here at the Reuter site to replace the coal generation capacities, and the storage is part of the overall package here. So the site selection was quite easily. We did a lot of different simulation studies where we compared different technologies, different dimensionings of the storage, and narrowed down the opportunities a little bit. The storage types, some of the storage types we heard before today were also under consideration, but due to the requirements and as well like the technology readiness level, we wanted to aim here at, we focused on tank storage, did a feasibility study where a lot of different aspects were considered. As I said, the dimensioning was investigated, but we did a lot of dispatch simulation studies as well with different scenarios for our future generation technologies to see how the storage performs under different conditions. Then which was quite important as well. If you have such a large storage, some soil screening to look at if the soil is suitable for building a large storage onto it, and what measures are needed, and then a hydraulic concept to see how the storage can be tied into our district heating system, because there are different points where you can connect them. And then as well at this power plant location, we have a three pipe system with two supply lines and one return line, where one supply line supplies a constant temperature of about 110 degrees, and the second one is operated under different temperatures according to the ambient temperatures. So that was quite challenging as well to see how to fit that into our system here. Yeah, then after the planning stage, obviously the establishment phase, which was about 1 year, the procurement, tendering, and at the end of this, the final investment decision, and followed by the realization phase where the tank, but all the surrounding systems was constructed, which was a little bit more than 2 years in total. Alone the tank filling was, I think, a couple of months or 6 weeks about, I think. So that took quite long, and followed by the commissioning and a lot of test runs before the tank was finally handed over to our operation unit. So this is a summary of the main value drivers, how we looked at the storage. On the left side, you can see we have many different opportunities to feed our storage. We have this power to heat units, 120 megawatts, which are mainly meant to transform excess electricity from renewable energies into heat when prices are low. We have as well CHP heat, which is sometimes not needed, which can be stored. And then we have these waste incineration plants. We have the sewage water heat pump. So all of this heat can be stored into the storage, which is a quite nice use case for a storage, but it makes it quite complicated as well. So the main value drivers in how we see it, I mean, it's very subjective and depends very much on the system which is connected to the storage, but obviously the highest value is by dispatch optimization to optimize the operation of your generation units, give them flexibility and the ability to react on market prices and decoupling from the actual district heating demand, which has to be supplied at any given moment. So there the value is obviously very high. But in addition to that, we have several additional value drivers which make this project quite interesting. We have reserve capacity, so we have a charging and discharging capacity of 200 megawatts here. So if we know it gets quite cold, we can charge the storage and use this as 200 megawatt of backup capacity. Otherwise, we would need to build additional generation units to do so. Then as well, we can bridge short-term outages of some of these assets. Hopefully in the future, this will not be such a big value driver, but right now we have these very old cold power blocks. So sometimes you have some unpredicted standstill periods, and then you can use the storage to fill in for these short-term periods. As well, you can use it in the overall context of the operating reserve for our power grid services, not standalone, but together with CHP and power to heat, we can provide services like this primary and secondary service to the power grid, and this can be optimized and improved with the storage. Additional value drivers are this flex value, which just means that you put a little bit more flexibility into the operation of your CHP and e-boilers for short-term price signals, which is not our main driver here, but it can be an additional value driver as well. And then generally, if you have redispatching, which is caused by surplus of renewable energies in the grid, and you have to switch on or switch off your power plant capacities, then you obviously can use your tank here, like to make this a little bit more favorable for you. And as I mentioned as well, you can use this for pressure holding, for this static pressure holding. If you have a pressure of about roughly 4 bar at the top of it, you can use it for this as well, if it fits to your district heating system. But this storage was deliberately designed to do so. So now to the monitoring, which is it's in operation, but it hasn't been ongoing for a long time, so that's why I cannot really present a lot of data here. But on the right side, you see the monitoring system, where you see the temperature levels on different heights of the storage. And we have currently a research project which looks into this operation together with TU Dresden and a software consulting company where the storage is equipped with fiber optic temperature measurements to have a detailed picture of the temperature in the storage, then develop a digital twin of it to do different simulation studies how to optimize the operation, especially to keep this boundary layer in between the hot and cold part of the storage minimal, and see how the charging and discharging operation affects that. And then as well, a pretty important aspect is the economic performance monitoring here, to see if the operation by the operation department is done as it should be, and if there are additional values which are left on the table, and if it can be optimized, which is something which is currently been done, because it's already running and creating value, but it can be optimized, and it's quite complex for our operating department to have this right from the start. Okay, thank you. Then here, quick summary. We have this new heat storage for flexibilization and optimization of our system, and which will hopefully reduce our CO2 emissions in the future by quite a bit. The main value creation is done here by dispatch optimization with the other generation units, but other value drivers exist as well. And operation should be monitored quite closely, especially during the beginning, to see that the actual operation comes close to what was initially planned for the storage. Okay, thank you.
All right, thank you very much, Julian. That was very interesting. I can see that there are questions in the chat, so you can just ask them, Damian, Jörg, for example, or others.
Yes, thanks. Very, very interesting presentation. I didn't get the difference, or to me, flex value and dispatch optimization sounded very similar, or at least in my mind, they seem very similar. Could you explain the difference between the two?
It's mostly the time frame it's done on. Like if you see, you can compare it to day ahead and intraday, I would say.
Okay, and so which one is which? And which one?
For us, the dispatch optimization is usually done 1 day in advance, and then you have shorter adjustments during the day. So that would be flex.
Thank you.
Yeah, my question is about the total power output of the site in comparison to the 20 megawatt of the storage.
The total power of the site, it's roughly 180, 250, 350 roughly, I would say, if I add this up here compared to the 200 megawatt of the storage.
So between 5 and 10% roundabout. Huh?
Yeah.
Yeah. Okay. Thanks.
Nasser, you have a question?
Yes, please. I'm wondering, like, if there is any potential for high temperature thermal energy storages, for example, that they can offer, for example, a lower storage or storage size, but then giving a higher capacity. Have you ever experienced any of the in your studies, something like that?
I mean, in this initial study, different types were compared, pressurized tanks, for example, as well. But in the end, this system had the best price value. And then actually on this side, there was a demonstrator for a molten salt storage. I don't know much about it, but I think it was running for about 2 or 3 years. But after this test phase, it was not followed further because it was just like rather small or very small in comparison to our overall system. And if you would want to scale it up, then you would have the very high specific prices, which doesn't make it very attractive in this case.
Thank you very much.
Thank you. There's one last question in the chat. It's time for the break, but feel free to stay if you want to ask questions for the two previous speakers. I hope it's okay if you stay a tiny bit longer. Franz is asking about how the tank was constructed, if you thought of any alternative, for example, concrete, and how did you make sure that the tank is not leaking out? I think this is quite straightforward.
Okay, I'm not familiar in detail with how it was constructed, but I think there was like a crane which kept the different parts of the storage in place, and another crane where the welding people were standing on. I heard that sometimes this work had to be stopped because of strong winds, but I think that's the general way it was constructed. I don't know if concrete was considered. I think there was this tendering process, where I don't think that the material was that much specified, but in the end, this is a steel tank is a very conventional technology, so this turned out to be the final solution.
Yeah, thank you. If I may add, just for the steel tank construction, there is a norm that defines the construction of such steel tanks, and there are tests that are required for the weldings that make sure that there will be no leakages. So that's how it's done. And then the insulation is some, let's say, regular building insulation. It can be wool, glass wool, or rock wool, or you name it. So depending on the level of insulation that is required. There's one last question asked by Alexander about an idea of the capex. You've already given one. It's 50 million, everything included. Do you have an idea for the OPEX?
No, actually, I don't have an idea for the OPEX, but I would guess it's quite small in comparison to the OPEX of the coupled generation units.
Yeah, there are the electricity price to run the pumps, but in terms of operation and maintenance, it's rather low. But it's hard to give a number for that.
Yeah.
Thank you, Julian. if there are any outstanding questions, feel free to raise your hands now. But else, I think everyone deserves a nice remainder of the break. So see you at 11:45.
All right, it's 15 to noon. But Alex, you can slowly, yeah, put your presentation on and slowly begin.
Okay. Can you see it?
Yes, not in presentation mode, but
yeah.
Yes.
Is it now okay?
Yes, it is.
Yeah. Okay. So I will present feasibility, design, tendering, and monitoring for a 70,000 cubic meter pit storage in Høje-Taastrup in Denmark. So first step was the opportunity. Where do we find the opportunity? And in my mind, it's always in the heat planning. Because if you make a heat plan, then you can see if you have possibilities, if you have resources for storing heat or not. So in the heat plan for Copenhagen, it's actually for the whole city of Copenhagen, which was prepared in 2014, there was stated that it demonstrates a large economic potential for investing in heat storage in the metropolitan area. So next step is to find locations for the establishment of heat storages in relation to grid connection and space for thermal plants. So that was the job according to the heat plan. If you look at the heating system in Copenhagen, it's there are 3 transmission companies. The blue one, that's Vex, it's for the western part in Copenhagen. And then there's the yellow one, which is CTR, is the central part of Copenhagen. And then the green one is Vestforbrænding, which is a plant that burns waste and distributes heat in the northern part of Copenhagen. So these 3 areas are then connected to distribution companies. And for instance, for Vex, there are, I think, 18 distribution companies. And the system is that the transmission pipes runs with between 19 and 120 degrees, and distribution systems are connected with heat exchangers, so they run with, for instance, 75-40. So that's a typical way to run the system in Copenhagen. And there's 4 CSP plants, and they are all with wood, and then there are 3 waste-to-energy plants. So actually there are only fossil fuels in the system for peak loads. So further calculations showed that if you could make a 70,000 cubic meters storage in Høje-Taastrup, and you could have 30 megawatts in and out, 30 megawatt coming from the transmission pipes, and another 30 megawatt when you discharge to the distribution system. Then it would be, so it looks like a possible solution, profitable solution. And investment should be around 74 million Danish crowns, and income about 6.3 million Danish crowns. So and income is 50% from saving peak loads and 50% from more efficient running of the CSP systems, approximately. So that was the idea, to serve the total system in Copenhagen with this storage and provide flexibility to the CSP plants and to save peak loads. Høje-Taastrup district heating found this area, and then the next step, one thing is economical feasibility, but it also has to be sustainable, and especially where we place the storage, we are not allowed to harm the area. So we are looking for groundwater conditions, and in this case, they were, I think it was 26 meters below. And if there were some protected areas, and that was not the case, protected fauna, that was not the case. It's a farm area, so if you look at the flora and fauna in Danish farm areas, it's very poor, so you cannot spoil so much. It was not a historical and cultural landscape, and we could see that groundwater was not a drinking water area. So influence of groundwater was of course, if you use district heating water in the storage, you have a very basic water which can include the groundwater, but in this case it was the same as for district heating water, so it was accepted. We could get rid of the waste water, and in traffic there was there's no special traffic to a storage in the operation period. Of course, in the implementation period there might be traffic, but here we are just beside a highway, so no further traffic problems, and people were not around. Still, it's a farm area and not vulnerable. And then there was a severe reduction in greenhouse gas emissions. So we could not find serious environmental consequences, and the result was that the project was feasible and could be implemented without environmental impact assessment report, even if you are near Copenhagen. Then in the design phase, there was first the excavation. The design, for the excavation, we had to find the storage geometry and amounts of soil to be removed. And we had to make details for penetration of liner, details for in and outlet, details for pump cellar, drainage details, principal diagram. So what you can see in the drawing here, that's how the storage is placed on the building site and how the pumping cellar is placed also in the building site. So it's one of the illustrations in the design phase. Another one here shows the longitudinal section of the storage, and as you can see, it's it's a very flat storage, and it's very long. And we have in and outlet in one end, and even then we think we can have a good stratification over in the storage. And this was also calculated during the design phase. Another part of the design phase is the liner work, including the lid. And so we had to calculate the amounts of liner to be welded, details for the penetrations also from the liner side, and for the lid construction and for dewatering the lid, and make a principal diagram. So this is just one detail for how to get rid of moisture from the lid. And another detail, how to make pump sumps so that you can get rid of rainwater. So this was quite detailed, described the storage and the details, but even then we didn't want this was not, you could say, just to take over. We wanted turnkey contracts, and if you look at the storage itself, we had 2 turnkey contracts. One for excavation in an outlet, concrete work and pipe work, and one for liner and lid. And each turnkey contractor must be responsible for all deliveries, building permits, detailed design, coordination with other contracts, and so on. It means that all responsibilities are taken over by the turnkey contractor. So what we did was to make soil work, dewatering, pump cellar, and so on for the excavation contract, and also demand specifications for membrane work and so on for the liner and for the lid. And then the entrepreneurs who are winning the contracts, they have to take over responsibilities and also to show us and the building owner the detailed design and have it not approved by us because then we take responsibility, but we have to have a chance to give comments. So that's the way we have made the tendering. For the construction phase, here's the earthworks, the soil works are nearly finalized, and you can see the liner work has started in the other end. And it's first it's a geotextile, and then it's a polymer liner. And in this case, it's a polypropylene liner. And here the liner is placed, and there's a protection liner. That's it's black. It's a PE liner, very thin, which is used as protection to avoid dirt when you fill water into the system. So you fill water below the protection liner. And what you can see in the foreground, that's the in and outlet. And what's special here is that the outlet in the top is only with one plate, because the other plate is actually the bottom of the lid to utilize the full capacity of the storage. And the same system is in the bottom. So this is before water filling, and then you start filling in water under the protection liner, and here we have filled in water nearly to the top, and it took one winter to fill 70,000 cubic meters of water in, because we wanted to have district heating water, and it has to be produced from the system in Copenhagen, and there was a limited capacity. After filling in water, the floating liner was implemented, and this floating liner was also a polypropylene liner. And why we have used polypropylene is that the temperature in the top of the storage will be 90 degrees the whole year round. And in the bottom of the storage, you could say the return temperature from the distribution system is around 45 degrees, so the bottom temperature will be around 48. So that's a temperature difference, but if you use what we used to use, HDPE polymer liner, then the resistance to 90 degrees is too low, so we had to use this PP liner. And it was developed by Agro and Linz University, and this was actually the first time it was used. So you can see it floats on the water, so you weld it on shore, and then you pull it over the water. And then you can build the lid actually similar to when you build a roof. So you start with insulation. In this case, you can see it later on, but there's two types of insulation in the system. So I think we have it somewhere. It's actually, there's first you have a polymer PEX insulation, and then you have a foam insulation, and on top there you have gravel and its sections. Before commissioning, there was a test part, and there was a cold test where different things were tested. So this is only to show that in this Pixie book there was several tests, but this is two of those where the first one was WEX supplies to Høje-Taastrup, and the next one WEX supplies to the storage, and then all those things had to be tested before commissioning. If you look at the economy, this is the total system, and it includes the storage, but it also includes connection pipes, transmission pipe to heat exchanger building, where heat is coming in from the transmission system and distributed sometimes directly to the distribution system and sometimes to the storage. And from the storage you can also distribute to the distribution system from this building. So here at first the soil expenses and design and supervision, and then storage and pumping station, so heat exchanger building and a district heating pipeline and electricity connection and water. So in total 12 million euros, and you might maybe compare to the 50 million euros for the system in Berlin, because in Berlin there was 2,750 megawatt hours. Here we have 3,300 megawatt hours. But in Berlin you had 200 megawatt in and out, and we have 30 megawatt in and out. And of course, if you have 200 megawatt in and out, all pump and heat exchangers and so on will be more expensive. But still, we think that pit storage will cost between half and 1/3 part of the tank systems. For the operation, we have calculated 160,000 euros per year, and half of that, or a little more actually, that's electricity cost for pumping, because we have calculated 25 cycles when this was recalculated, and this will give a payback period of 12 years and internal rate of return of 7.5%, if we expect a lifetime of 20 years. There's a monitoring system, and this is made by Danish Technical University, and if you look at the picture on the right side, you can see there are actually monitoring of the temperatures in the storage, and there are two of those, one in each end, and then we can see if the stratification is precise or not, and it's very precise, even if you have in and outlet in one end. We have a temperature difference of, I think, less than 1 degree. And then, of course, the soil temperatures are monitored, and moisture in the lids, and heat flux calculating what's coming through the lid. So here's results from we started the storage in February 23. So this is from the first year, and you can see it's charged and discharged all the time. And this is regulated from one place in Copenhagen where all 7 CSP plants are regulated so that you always produce heat on the cheapest plant. So if you need to stop your GSP plant because electricity prices are too low, then you can discharge the storage, and opposite when you have nice electricity prices. So we are decoupling actually CSP plants from the heating system, and in this way providing flexibility. If you look at the efficiency, second year of operation, it was 89% during the year, and it's actually calculated to go up to 95%. But the first years we are heating up the surroundings. That's one reason why it's not 95. Another reason is that we don't have 25 cycles, we have around 10 cycles. So, but it's coming up every year. So that was all from my side.
All right.
Thank you very much, Alex. Are there any questions from the audience? We have a couple of minutes. Alexander, would you like me to read your question, or would you just like to directly ask Alex?
Hi. My question is about the property costs. If we compare the application of thermal energy storage in urban areas to support district heating, we should include the property costs of the different types of thermal energy systems, storages, and it would be interesting if we put the plant of Alex in the center of Copenhagen. What would be about the property costs?
We will never do that.
Okay.
But of course, in this case, it's farmland, and then the property costs are low.
Of course.
But there might be other, but we are always looking for this kind of sites. But in Germany, if you ask people, they say, we have to pay 200 euro per square meter. So if you calculate 100,000 cubic meter storage and say now you have, instead of what we used to pay in Denmark, you have to pay 200 euro per square meter, then it's maybe 50 euro per cubic meter storage you have to add, 50 or 60 euros per cubic meter storage for such a storage. Even then, it's half price of a tank.
Mm-hmm. I see. But maybe the property cost, for example, for the tank energy storage is higher in Berlin, no?
Yeah, it could be higher than 200 euro per. Yes, that's right. I would never place a storage like that in the city of Berlin. I would place it outside Berlin and then make a transmission pipe. But if you ask people in Berlin, they say, we cannot place this in Neubrandenburg because it's outside Berlin. Well, if you are that stubbish, then you have to pay for a steel tank.
I see. Thank you.
Thanks, Peter.
Yeah. Hi, thanks for the presentation. I have a question regarding the dimensioning of the storage. In your plot of the charging and discharging, it looked like the full capacity was only used 5 times in the year. So only 5 times the storage was completely full. Would you say that a bigger or smaller storage could be more economic?
Yeah, I think this size is economic, but you don't fill up the storage totally, because you need all the time to have flexibility so that you can fill more and you can discharge. So actually the optimum is not to have a full storage. The optimum is to have capacity to the flexibility.
Okay, thanks.
I can complement by saying that it's a lot of small charge and discharge cycles that are happening. So you would never go for a full complete charge and then a full complete discharge, but rather small cycles of partial charge and discharge.
Yeah, it's when you run this system, there's a weather forecast of 1 week, and that's actually you could say that's the main charging discharging the next week. But then during the day, there will be I think up to 6 times you will get new charging discharging orders. So the system there's a long term 1 week weather report, you could say, and then hour by hour control. Niels had a comment, I think.
Yes, that's just to add that the storage in Høje-Taastrup is some kind of a pilot storage to test the technology, and they're considering to building a much larger storage at a later time. So there are enough space for a larger storage capacity in the Greater Copenhagen district heating system.
Yeah, thank you.
But the reason why this is possible, that's also that the transmission pipes are actually, I think, 35 to 40 kilometers west of Copenhagen. So that gives some possibilities to add storage to the system, because Copenhagen is connected to Roskilde, which is a quite large city, and in between there are gravel pits from rock wool from older times, and large areas which are now, you can see, recreation areas where you could have a storage also.
Yes. So we are now in the wrap up and open discussion part of this webinar. It's still fine to ask some questions, but I will be trying to direct them a little bit. There are questions in the chat. Zishan is asking about deserts as an option for installing these kind of plants. I don't know what you mean by this. Would you like to further detail your question? Okay, we'll get back to this afterwards then, because I don't really understand this question. But then Voloshin is asking which form of thermal storage would be more suitable, acceptable in a big urban environment, urban development setting, and I think that's something that's a bit cross technology question. So that's interesting for all the previous speakers to maybe give some insights into this. I don't know who wants to start. If Benjamin or Alex want to give it a go. Alex.
Or Alex.
Okay, yeah, and then Alex first, and then Bas.
Okay. Well, it depends. If you have deep ATES possibilities you can make, like we saw the example from the Netherlands, that will be the most feasible way to do it, and it doesn't take very much land. So that's, but it's not so often you can find those places. So then you have to look for what are the possibilities for PTES, or yeah. So yeah.
Thank you, Bas.
Already a good answer. Yeah, it strongly depends on the location where you are and what kind of what's exactly needed for the storage. How should it also be used? Is it long term, short term? But also what are the hydrogeological conditions indeed? But also what, how much surface is available. And of course, the advantage of the ATES system is that the space on surface and also in subsurface is very limited. So that could be very useful in crowded city areas. And that's also what you see for the normal ATES system, that it's often applied in the city centers without any problems. So yeah, large PTES needs, of course, space and yeah, but if it is available, then it can be very useful. So I think it should be decided from case to case.
Thank you. I think that's a good summary of the different things that should be considered. You also have to remember that a lot of these heating centrals, they have a bit of ground available, and very often they try to put a tank thermal energy storage on the site. So that's let's say that's also an option, but it is more expensive per volume considered compared to an aquifer or a pit or even a borehole thermal energy storage could be an urban alternative as well. So Zishan has precised a bit the question. Now I understand a bit more. So the context is we're situated in Pakistan, and there is a lot of land that is in the form of desert. So the cost is very little. So the question is whether deserts are a good option, and even though the temperature conditions are harsh. Does anyone have an idea on this? Maybe Alex. I can give as an example that there is a pit thermal energy storage that was built in Tibet. Actually, several pit thermal energy storages have been built in Tibet, coupled to solar district heating for seasonal storage of heat. And it's in rather desertic areas at a very high altitude, so rather cold conditions. But this didn't pose any problems in terms of construction. But does anyone have further insights into this question? Yeah, Bas?
I think the transport of the heat from the desert to the end user and from the surplus of heat to the storage, that's, I think, a very important cost element. So I think that should be considered, and that's often also breaking some business cases if you have a long distance or a big distance between the storage and the users. So I think that's something you need to investigate if you can do that in a more efficient way, but else it can be a business case killer. That's my experience.
Thank you. There is, yes, Alex, you want to add something?
Yeah, if it's for heating, then you have to be aware where the desert is. If it's in Mongolia, so it might be a good idea. But if it's in Pakistan, I don't think the heating demand is so high. So, yeah.
Yeah, the application, of course, should be considered. There's one last question. We should go through it quite quickly because I want to ask two further questions for the open discussion. for the PTES in Høje-Taastrup, the question is, why didn't we go deeper into the ground for better stratification in area usage efficiency? Is it because of groundwater or construction issues? I think Niels Frank can answer that question.
Yes, the reason is this available space. We are limited by the highway to the south and a big water pipe to the north. So it's a small stripe of land that was available. And also the soil conditions, we were not able to make the slope steeper than we have done here. So of course, we would dig deeper. It was possible, but it was not possible on this side.
Thank you. So for the open discussion, I will start by asking a question that is echoing the conclusion from Benjamin earlier about his ATES study in Germany, which drew a bit of a dark picture, I would say. Not a lot of potential, it seems, at least for large ATES, as a standalone at least. And one of the reasons was that the distribution was often done at high temperature, and that doesn't correspond to the limited maximum temperature that you would put in an ATES. But I'm thinking it might be possible to couple it differently. So if you look at the example that Per-Alex gave, the PTES is connected to the transmission grid, which operates at 105 degrees Celsius approximately. But the discharge is being done in the local distribution network, which is at a lower temperature range. And in that case, it doesn't matter that the temperature cannot go higher than 90 degrees Celsius. So that's one way of solving this. Bas, do you agree with this? Do you also see in general a very big difference between the subsoil conditions in Germany and in the Netherlands, and that could be one of the reasons why this study came to this conclusion? What are your analysis of this issue? And if Benjamin is still here, feel free to jump in as well.
That's a very interesting question. I think Benjamin has investigated the part between 500 and 1,500 meter, and I know in the Dutch situation that this part is also a very unknown unknown part of the subsurface because there are a lot of drillings in the first 100, 200 meters, and then for the deep geothermal or gas or oil drillings, they quickly drill to 2 kilometers depths, but they forgot to measure all the subsurface data between 500 and 1500 meters. So I can imagine that it's still unclear what is exactly the potential. So I agree with the conclusion of Benjamin that more drillings or investigations are needed to assess this potential. And now for the Dutch situations, we have at least good aquifers in the first 1 to 300, 400 meter, which gives already a big potential for heat storage. And the more shallow aquifers, I know that when you go a little bit deeper to hard rock, so sandstone formations, that the storage efficiency is much more higher in these formations. So that's still interesting to investigate and to check if you can apply it. But often a lack of good subsurface data is one of the reasons for, I think, a very careful conclusion as Benjamin drew.
Thank you. Benjamin, you would like to complement this?
I think Bas already answered the question very good. One of the reasons why we focused on the depth of 500 to 1,500 meters was that we expect higher surrounding temperatures, increasing the efficiency. Plus, we expected to have less interactions with drinking water horizons. So that these were the reasons. Of course, Bas is right that there are aquifers which are more shallow. And the first high temperature ATES in Germany is also developed in shallower depths. Also in Berlin, it's I think around 300 to 400 meters depth, if I'm not all mistaken. So there are additional potentials in more shallow areas, but for the reasons I explained in the beginning, we focused in our assessments more on the deeper grounds.
Thank you. So maybe as a general takeaway, when you're talking about ATES, it's also very important to know at what depth you're looking at the subsoil, because you can come to very different conclusions. May I also add, Benjamin, that in your study, you haven't looked at the possibility of making use of the cooling capacity of the ATES in the framework, and that could be an added benefit to the usage of an ATES in these cases that you looked at. So again, a bit of mitigation on the conclusion and the potential. When you make a specific technical study, it has some assumptions, obviously, because you cannot study everything. So to put things a bit into perspective. Yeah. I have one last question. I'm going to try to involve most of the speakers from today. Seeing the presentation from Julian in Berlin, I think it's a surprisingly small tank thermal energy storage capacity we have, even though it is. It was, when it was built, the biggest TTES in the world. Now I think it's been beaten by a TTES in Munich that was 57,000 cubic meters. But if I just give some rough ideas, in Aalborg, there has been 4 times 50,000 cubic meters that have been built, extra to 2 times 25,000 cubic meters, and they're charged and discharged with a thermal capacity of 500 megawatts. In Aarhus, they're going to build 2 times 50,000 cubic meters. In the greater Copenhagen area, there are 2 times 22,000 pressurized tanks and 1 time 24,000 cubic meter tank with a 330 megawatts output power. Also, there's this pit thermal energy storage with 30 megawatt output power. My question to you, Julian, is there further development of thermal energy storage capacity planned for Berlin? Because as you mentioned, it's a very big network, and I'm just a bit surprised to see that it's only this one big storage that is being used.
Can you hear me? Switch my
yes, we can hear you.
Oh, perfect. Yes, you're right. I mean, we have the different technologies and they all have their characteristic. I think in this case, much more interesting than the storage capacity is the power of the whole thing, if you combine it with power to heat optimization. So that was the focus here, and I think it's a strength of the tank storage technology to do short-term storage with high power. But as I said, like the initial idea of this project dates back to 2011. So obviously right now we are planning new projects with additional capacities. So we are definitely going for more short-term storage capacity, probably in the form of another tank, but looking into long-term storage as well. The aquifer storage, we already heard that aquifer storage is probably a very good option in Berlin, which works, and maybe pit storage as well, which could be for us an interesting combination of these large storage capacities with higher power rates. But for this, we are, as we heard before, it's unlikely that we have this within the city borders. We are thinking about combining this with the integration of heat sources from the surrounding area of Berlin. There we have, for example, data centers and other wastewater plants. And if we connect these to our grids, then we will build connection lines to the outer city anyway, and then we can probably build pit storages there on the way. So, but these are projects, right now we were focusing on this transformation phase until 2030, and these are post-2030 projects.
Thank you very much. I think that sums up very well. Alex, you have maybe a short remark because we're at the end.
Yeah, just to say that in and outlet capacity also in pit storages can be very high. So we have one in Odense, 150 megawatts, and we could go higher if that was needed. We calculated in Aalborg 300 megawatts in a earlier project.
Thank you for specifying this. Thanks everyone. So before I finish this, Romain sent in the chat the evaluation form. Please fill it in. It's very small. It's just for us to know what we can do better. So have a look. It's in the link is in the chat. Then I will come back to what Julian was saying. That is extremely important takeaway from what we've been seeing today for all the technologies. The proper system integration is extremely important when you design this kind of thermal energy storage. What it is coupled to, what it is intended for, the temperature ranges, the cycling that you need, all of these parameters are extremely important and will impact greatly how your storage looks in the end. There is no one size fits all. You have to make a specific study every time you have a thermal energy storage project. But that's why we have all of the experts of Task 45, amongst other things. So if you do have a concrete project and you would like to get some help, reach out to the experts of our group, and we will redirect you to the appropriate people. Thank you so much to all presenters. Thank you for the audience for their questions. It was quite interesting. I can see there's one question left in the chat. We will see if we can treat that question probably in a Q&A session. So this is the planning for the upcoming sessions. You can see that in January we'll have a new Q&A session, also coupled to these technical topics. Then in March there will be another Q&A session, and then our next set of Q&A session and webinar will start in May next year, and the focus will be more on practical experiences with large thermal energy storages. So we will dive even deeper in the practical aspects of usage of large thermal energy storages. In the meantime, thank you so much again. Merry Christmas to everyone. Enjoy the end of the year, and we'll see you in 2026. And again, please fill in the form. That would be a good Christmas gift for us. Bye-bye.
Thank you. Bye-bye.
Bye-bye. Thank you.
Bye.
Bye-bye. Thanks.
Thank you. Bye.